In the previous video on discrete convolutions, we have ascertained one very important result, which is pictured right here. The fact that when you multiply two generating functions, which again encode a sequence as coefficients of an infinite polynomial, we saw that when you multiply two of these generating functions together, what you get is really an operation on the two sequences called a discrete convolution. And you can multiply them by using the dot, or we alternatively can use the notation of this asterisk or star as a marker of discrete convolutions. And so the formula is here. When you have a of x as a generating function that encodes an an sequence, and you have b of x that encodes a bn sequence, then a star b of x is its own function c of x, which has the following generating function. And from this result, we also used the geometric series a lot to then show a certain other result, which is pictured over here. We discovered that a more general higher power form of the geometric series, 1 over 1 minus x to the k plus 1 power, is really equal to the sum, as n goes from 0 to infinity, of n plus k choose k x to the n. And when we want to have it as just a k term, it's n plus k minus 1 choose k minus 1 as a little shift. So now we also mentioned that we would look at combinatorics today, which is the study of counting. And so what motivates this? Well, for instance, look at what we have as coefficients here. We have combinations, right? And we saw this with the binomial series as well. Over here, a combination. So this might encourage us perhaps to look into combinatorics and see how generating functions can help solve us problems in that domain. Now, in as much as what we've done so far, we noticed that combinations have only been discussed in the context of coefficients of generating functions, but we've never given them the true meaning that they deserved, the true recognition that they deserved, as they're central to the study of combinatorics or counting. So let's define formally what a combination is. A combination, or n choose k, is defined to be the total number of subsets of a set size n that are themselves size k. So we're basically answering the question of how many subsets size k can we make from a set size n. And so the formula for this, it turns out to be n times n minus 1 times n minus 2 times n minus 3 all the way down to n minus k plus 1, whatever k is, and we divide that all by k factorial. Now the combination, which is again denoted n choose k here on the far left, is a character of many names because it can go like this. You can also define the numerator to be called n to the falling k, or n per mute k. And in general, this is the exact same thing as n factorial over k factorial times n minus k quantity factorial. So once again, it's important to keep in mind all these different possible definitions, even though they all mean the exact same thing, and this is really just your own decision. Personally, I like to use the first definition here because it is the most clear in terms of what we're doing. So let's now get into some more ideas behind combinatorics. First of all, you can look at how we can answer questions and learn identities using something called a combinatorial proof. For example, a combinatorial identity might be n choose k is equal to n choose n minus k. And while you can prove this by expanding this out in terms of its definitions, of its many different kinds of definitions, and solving them to equality, that's not very creative, and it doesn't show much like real discovery. So what do I mean by that? We can also prove combinatorial identities with what's called a combinatorial proof. So I'm going to write combinatorial proof. And what a combinatorial proof is you essentially ask a counting question, all right? And the counting question just asks you how many ways there are to count a certain thing. So for example, in this situation, we can say how many ways are there to choose k objects from n? And the answer to that the left-hand side provides is n choose k by definition. But what about the right-hand side? Well, instead of choosing the k objects to include in our picking, what if we choose the n minus k to leave out? And so if you choose n minus k from n to leave out, then you've automatically constructed your set of objects that you've included, the k objects you've included. So the right-hand side also answers this question equivalently well of how many ways there are to choose k objects from n. And so therefore, because these two sides answer the question in their own ways, they are equal in value. So that's an example of combinatorial proof. Now, other combinatorial identities can also be determined from combinatorial proofs. For example, this is called Pascal's identity. This is a very important one that describes the recursion and the recursive nature of combinations. So Pascal's identity. And in fact, you can see n choose k as a sequence of two different variables of n and k. And so it's almost like a multivariable sequence. So far, the sequences we look at with generating functions are all univariate. They depend on one parameter, n or I, so a sub n or b sub I. But you can look at combinations as bivariate sequences. So that's an interesting thing to keep in mind, but it's not very crucial for our learning and purposes here. So this is Pascal's identity, and you can prove this in one way. We're not going to go over that. You can also have this identity. This is another example. N choose m times m choose k is equal to n choose k times n minus k quantity choose m minus k quantity. And this is basically, you can prove this in your own ways. For example, the way this is determined is asking how many ways there are to pick a committee of m people with k leaders. So if you pick your m people for your committee, it's n choose m out of n people. And then out of those m, you pick k leaders. You could also pick the k leaders right away, n choose k, and then pick the rest of the committee members around that. So you have to subtract the k you've already chosen from the pool that you can pick from, n minus k as your total, and then pick your m minus k remaining members of the committee. So that's basically one way to answer this question. Now, this is all interesting about combinatorial proofs, but where do the generating functions show up? Well, it turns out that there are some identities that involve combinations that are very much not obvious and don't seem to have any physical meaning, yet they still hold true. So what do I mean by that? I'm going to scoop back up and find ourselves an identity. Right here. We can show combinatorially that n plus k minus 1 choose n on the left-hand side is equal to minus 1 to the n times minus k choose n. And so you might wonder, this makes absolutely no sense. How are there any ways to choose n objects from negative k? Why do we have a minus 1 to the n term? And that's exactly what I mean when the combination in its theoretical definition doesn't have a physical meaning, yet the algebraic definition that we saw earlier on, right, which was over here, all the way back here, it still holds true, and we can extend it to negative numbers and to fractions even. So, where do we go? Okay, we're back, right here. So, how would we go about proving something like this? And recall from the previous episode that I encourage you to think about the connections between that generalized higher power form of the geometric series and the binomial series right over here. And so we're going to employ both of them right now and determine how we can determine or prove that identity that we showed. So we have the following two identities. 1 over 1 minus x to the k power is equal to n plus k minus 1 choose k minus 1 x to the n, all summed as n goes from 0 to infinity, which is already the left-hand side of our proof, of the statement we want to prove. So what we seek to do is manipulate the binomial series to see how we can turn it into a short form resembling the geometric series higher power of k. And this is exactly where we, again, have to remember the idea of 1 plus thing, right, to the k power is equal to the sum, as n goes from 0 to infinity, of k choose n, and k can be another thing. But here we replace x with thing, so we do thing to the n power. So it's very important to keep in mind that composition can apply to any function, and you can do it whenever possible, as long as if you're trying to convert and use actual values and plug them into your series short form, that it's within the radius of convergence, or your interval of convergence. So how do we change the binomial series into this form over here? Well, let's start with 1 plus x to the k. Okay, and that's equal to, of course, sum as n goes from 0 to infinity of k choose n, x to the n. Now we want 1 minus x. So what if we just replace the 1 plus x with minus x? So we have 1 plus, in parentheses, we have minus x. And then instead of having k in the numerator, or this entire term in the numerator, we want in the denominator. And recall that this is the same thing as 1 minus x to the minus k. So let's replace the k with minus k. So what we get is the sum, n going from 0 to infinity, of the combination minus k choose n, which again doesn't seem to make any sense, but we know that there will be some algebraic meaning. And then we have minus x to the n, which looks like this. All right, and we can split this into minus 1 to the n times x to the n. So let's do that right now. So we have minus 1 to the n, like this, x to the n. And look, right away, 1 plus minus x to the minus k Well, this is all equal to 1 minus x to the minus k, which is, in fact, our higher power geometric series. And since they both have the form x to the n over here, using our blue highlighter, we have a sum as n goes from 0 to infinity on both of the structures. We have x to the n on both, which means that the coefficients must necessarily be equal. And so there you go. We've basically determined that the formula that we showed above, n plus k minus 1 choose n, is equal to minus 1 to the n minus k choose n, is true. But wait, we have k minus 1 in the denominator, quote unquote, here. But remember, with the formula we determined below, of the reflection formula, n choose k equals n choose n minus k, we cannot forget that n plus k minus 1 choose k minus 1 is equal to, and I'm going to write this in a place where it's more visible, right here. So n plus k minus 1 choose k minus 1 is equal to n plus k minus 1 choose top minus bottom, n plus k minus 1, like this, minus k plus 1 now, because we have to distribute. So the k's cancel, the 1's cancel, and you have n plus k minus 1 choose n. So the formula holds true. So that's one example of how generating functions are being used to determine certain combinatorial truths, even though they may not seem to have any physical meaning. Now, let's look at some real problems in combinatorics. For example, let's look at the ways there are to distribute certain objects to certain people or certain entities. And since we're already nearing the holiday season, I'm going to use a Christmas time themed example here, which we've come up with here at Josh Academy. Suppose we have n unique carrots. So n unique carrots. And say we have k of Santa's reindeer. So k reindeer. I ask, how many ways are there to distribute these n unique carrots amongst the k reindeer? And so we're going to use a principle of combinatorics here that lets us answer this by multiplication. So let's look at the first unique carrot. So first carrot. How many reindeer are there options to distribute this first carrot to? Well, we have k choices. Correct? K choices. Then how about the second carrot? Well, it doesn't depend on the first carrot. These are independent kind of assortments. So there's also k choices. K choices. And you can see how, with this logic, even the nth carrot has k choices of who we can distribute it to, to whom we can distribute the carrot. So k choices. So we use a principle in combinatorics called the principle of multiplication to multiply everything together. And so that means the total number of ways there are to distribute these k or these n carrots to k reindeer, where these carrots are all unique, is going to be k to the nth power. Okay, not too bad, was it? Now it turns out this problem gets way more difficult when you cannot distinguish between the carrots. So here's our second problem. You have, suppose, n identical carrots, or indistinguishable carrots. So n identical carrots, and we still have k reindeer that are also themselves unique. Wonderfully unique. So now we ask how many ways there are to distribute these n identical carrots to k of Santa's reindeer. And here's where we have a beautiful, very clever generating function solution. We can consider every single possible case of how many carrots each reindeer individually gets by encoding them into generating functions. So for example, for the first of our k reindeer, we can have either 0 carrots. So x1 is the number of, x1 you can think of as the reindeer. And the power of the x1 variable is going to be the number of carrots he gets. So you have x1 to the 0 power means that reindeer 1 gets 0 carrots. x1 to the first power means that reindeer 1 gets 1 carrot. x1 to the 2 power means the reindeer 1 gets 2 carrots. So on and so forth, right? Adding that to x1 to the nth power, where essentially this means that reindeer 1 gets all n carrots. And then you can repeat this for every other reindeer. So x2, x3, all the way up to xk. So xk to the 0 plus xk to the 1 plus xk squared. I'm trying to make it clear here. Plus so on and so forth. Xk to the n. Where, of course, once again, this bottom situation means either reindeer k gets 0 carrots, reindeer k gets 1 carrot, 2 carrots, or all n carrots. Now, what happens here is we can multiply all these together to get the generating function of our total number of ways to distribute the carrots. Now, you might still be confused. How does this work? So, yes, you're fair to be confused in the moment. Let's suppose we have, for example, 3 reindeer, and 8 carrots. Then one possible distribution of these 8 carrots, assuming they're all distributed, is x1 to the 3rd power, x2 to the 4th power, and x3 to the 1st power. What this means is reindeer 1 gets 3 carrots, reindeer 2 gets 4 carrots, and reindeer 3 gets 1 carrot. All right? Notice how when we do this, no matter what, the total number of carrots remains 8. That's the sum of the exponents here. And so then to get every possible case, because this is just one case of the possible distributions, to get every case, we must look for the coefficient of the x to the nth term in the product generating function of each of the individual case generating functions for each reindeer. So, for example, in this simple case right here, the short form of the case generating function for reindeer 1 is 1 over 1 minus x, as we know, as a geometric series. The short form for the nth reindeer then is also, or the kth reindeer, is 1 over 1 minus x as well, because we don't just have any conditions or discrimination here. So then we have a total of k reindeer. So when we multiply all these generating functions together, what do we get? We get that the total product is 1 over 1 minus x to the k power. And so we know that we're looking for the possible sum total of every case where, for example, you have n carrots distributed, right? Because you have n carrots total, always, to distribute. So that means we're looking essentially for the coefficient, using our notation from the previous episode as well, in square brackets, the coefficient of the x to the nth term in c of x, our counting generating function. And c of x is, again, equal to 1 over 1 minus x to the k power, because it's the product of all of our individual case functions. So what is this? Well, we know what this is because we know that the coefficient associated to this, we just saw it. It was equal to n plus k minus 1, choose k minus 1. So that means, ladies and gentlemen, that the total number of ways there are to distribute, in general now, not just a reindeer example, but the total number of ways there are to distribute n indistinguishable objects amongst k bins or entities is going to be given by n plus k minus 1, choose k minus 1. And so you can see how generating functions helped us answer this question in a very clever way. And this is especially beautiful because it turns an algebraic argument into a partially visual one. 3, 4, and 1 do all add up to 8, but they're also a way of imagining how every single reindeer gets a certain number of carrots. So that's one very cool thing to think about. But wait, there's more. Because this generating function approach to counting such complex counts still works when you change the conditions of the problem. So in this example, we uniformly at random gave out all the carrots to all the possible reindeer in any possible combination, which gives us a total number of ways of n plus k minus 1 choose k minus 1. Now, let's have a more involved example with numbers. So suppose we have 19 identical carrots. So 19 carrots, right? And then we have, say, 9 reindeer. 9 reindeer, including Rudolph. Okay? And all of Santa's reindeer. So suppose Rudolph, right, which we can call R, is Santa's favorite. So he gets at least 3 all the time. So R gets greater than or equal to 3 cookies, or not cookies, carrots each time. I'm thinking about Santa already. Comet, on the other hand, it turns out that Comet cannot get more than 2 carrots, or else he starts feeling sick. So C gets less than or equal to 2 carrots. All right? All the other 7 reindeer get same treatment, essentially. They don't have any issues or special priority. So then, in this situation, how many total ways are there to distribute the carrots? Well, remember, if there weren't any conditions, then n equals 19. And then we had k equal 9. And so the answer to this would be 19 plus 9 minus 1. Choose 9 minus 1. And this is equal to 27 choose 8. Theoretically, if this were a normal question without any conditions. But it's not. So once again, we have to create case generating functions, individual generating functions that represent each deer. So for example, Rudolph gets at least 3 always, which means that he cannot get 0, 1, or 2 cookies, or carrots, So that means that there's no x0 term, x to the 0 term, x to the 1 term, or x to the 2 term. So instead, you start with the case generating function xr to the 3rd power plus xr to the 4th power plus xr to the 5th power, so on and so forth, until really xr to the 19th power, because he could get all of the carets. But then this goes so on and so forth, but we don't care about the higher order terms because, we're paying attention to the coefficients here of the generating function at a particular point. All right, so that's Rudolph. That's Rudolph's case function. Now what about Comet? Because that's the other complex situation. He can get less than or equal to 2, so he gets at most 2. That means he gets either none, so xc to the 0, plus xc to the 1, plus xc to the 2, because he gets 2 maximum. And that's it. The generating function ends there. All right, and all the other reindeer, they have normal cases. So essentially what that means is that we basically have the same situation. We have 1 plus x squared, so on and so forth for the other 7 deer. So it's 7 of those. It's the 7th power. So when we multiply all of this together, what do we get? Well, we get, first of all, x cubed plus x fourth plus x fifth all the way up. This can be rewritten as the following for Rudolph. This could be the geometric series 1 over 1 minus x, subtracted from that the minus 1 term, the x term, and the x squared term. So let's rewrite it like this. And then what we can do here is we can bring everything under one denominator. So you get, or you factor it out essentially. So you get 1 over 1 minus x factored out. You get 1 minus, you have to multiply by 1 minus x for here. And so 1 minus x times minus 1 is going to be minus 1 plus x. So you have 1 over x times, this becomes 1, all right, minus 1 plus x. And then here, the x term becomes minus x plus x squared by multiplying by 1 minus x over here. And the next term becomes minus x squared plus x cubed by factoring or distributing the 1 minus x across the x squared term. And so this is very nice because look, you have 1's cancel, x's cancel, x squared's cancel. So what really this becomes is x cubed over 1 minus x. All right, so let's throw that in here. So when we multiply this, x cubed over 1 minus x, by x to the 0 plus x1 to the x2, then what do we get? We get x cubed times x to the 0 is 1, plus x to the first is x, and x squared is obviously x squared. And then we have the 1 minus x from the Rudolph case, and 7 more geometric series. So we get a total of 8. So it's 1 over 1 minus x to the 8th power. Okay? This is our c of x, our counting function. And essentially what we're looking for here is, since we have 19 carets, we have the coefficient of the x to the 19th term in c of x, our counting function. So this is basically the general principle that guides these kind of questions. So what do we do here? Well, let's split it into 3 cases. First of all, we can distribute the x cubed term here into the 1x and x squared. This becomes x cubed plus x to the 4th plus x to the 5th, right? Like this. And then we can distribute that across the 3, or we can distribute that across the 8th power geometric series. So this becomes x cubed times 1 over 1 minus x to the 8th power plus x to the 4th, 1 over 1 minus x to the 8th power, plus x to the 5th, 1 over 1 minus x to the 8th. And so we know that the formula for this, we get the series form of 1 over 1 minus x to the 8th power is sum as n goes from 0 to infinity of n plus k minus 1. In this situation, we have n plus k is 8, so minus 1 is n plus 7. Choose k minus 1 is 7. So n plus 7 choose 7, x to the n, but we have to throw the 3 in there. So we get x to the n plus 3. Then the next function is going to be similar. I'm actually going to reproduce this because it's going to be the same form, except the coefficients, the powers of x to the n are going to be different each time. So we have this as a result, like this. Except here, because we have to multiply the x to the 4th power in, this becomes x to the n plus 4. I'm going to color code these actually as well. So x to the n plus 3 here. And then here, because we have the x to the 5th term, we have to multiply that in over here and get x to the n plus 5. which means that even though the total coefficient is going to be 19, we have to account for each of these n's individually to make sure that the total coefficient becomes 19. So, for the first generating function, at which n value does the coefficient of c of x equal 19? Well, it's going to be when n equals 16, because that means that x to the 16 plus 3 is 19. So n equals 16 over here. We add that to the case where n is equal to 15, because that's when we achieve 19 in the exponent here. And we add that to the case where n equals 14, because that's when we achieve 19 in the third term. And so ultimately that means the answer to our question of how many ways there are to distribute the 19 identical carrots to our 9 reindeer, with 2 of them having special conditions, turns out to be the following answer. It becomes 16 plus 7, which is 23. Choose 7. We add that to 15 plus 7, which is 22. 22, choose 7. And we add that to the last one, to 14 plus 7 is 21. So it's 21, choose 7. And ladies and gentlemen, that is the answer. Look at how what a seemingly very complex question became much more simple to solve with generating functions. And that's just such a beautiful solution. And I love these kind of combinatorial questions that you can answer with generating functions. So once again, we've seen how generating functions have beautifully solved such a difficult problem. Next up, we will be exploring probability, which is a direct offshoot from combinatorics, because we will have to need to know combinatorics, at least to some degree, to know the probability. And then we'll see how generating functions play into computing certain aspects of probability that we want to know about. So I'll see you then.